So good evening. Do you have any doubts from the previous lectures? Okay. So today we will be starting with some transforms. Okay. So we will be very quick in these transforms, especially the Fourier series, Fourier transform, discrete time Fourier series, and then from uh, discrete time Fourier transform, and then from discrete Fourier transform we will be looking into some numericals. Okay. The reason being this discrete Fourier transform and Z transform, they are being used in analyzing digital signals and systems. So because of that, we will be concentrating more on the discrete Fourier transform and the Z transform. In between, we are having the Laplace transform, which helps us in analyzing the continuous time signals and systems, but it is related with Z transform. Okay, so usually when we will be looking into the designing of the filters in the digital domain, we will be seeing that the concepts of the Laplace transforms are being used to develop the digital systems, and hence the understanding of this Laplace transform is very much important. Okay, so let's start with that. I hope all of you know what is a Fourier series. What is a Fourier series? What is the definition of the Fourier series? Okay, anyone? No? Are you sure it is the Fourier series? That's what I am asking. Is it the case in the case of Fourier series? The Fourier series says that any periodic signal, they can be represented with a series of sinusoidal signals. Okay, so these sinusoidal signals, they basically, we have two types of periodic signals. Basic periodic signals, that is the sinusoidal signal and the complex exponential signals, these are there. So these type of these two basic periodic signals, they can be used to analyze any periodic signals. Okay, so this is the definition. So if you look over here, a periodic signal, it is basically a linear combination of harmonically related complex exponentials of the, and it is given in the form of xt equals to summation of k equals to minus infinity to infinity ak e to the power j k omega naught t. Okay, so this is your Fourier series equation. Okay, the main important thing over here is that over here we are talking about the periodic signals. Okay, say for example square signals, say for example these triangular signals, say for example the sawtooth signals. Okay, so the Fourier series says that we can reconstruct any periodic signals with the help of a series of sinusoidal signals that are harmonically related to each other. Okay, so when we talk about these harmonics, say for example, if we are considering a 50 hertz signal, then we will be having some frequency components, or the frequency component associated with the 50 hertz signal. That means 50 multiplied by 1 is 50, then 50 multiplied by 2 it is 100, then 50 multiplied by 3 it is 150. So the frequency components at 100 hertz, 150 hertz, they are regarded as the harmonics of the original frequency component. Okay, so 50 hertz, it becomes the primary frequency or the fundamental frequency, and then when we start multiplying that fundamental frequency with uh, the values of 2, 3, 4, we get the harmonic components of that fundamental frequency. Okay, so if you look into this equation, which is another representation of the equation which I showed you a few moments back. So over here, if you see, we are having xt, and then we can see it is a combination of various sinusoidal signals. Okay, apart from these sinusoidal signals, we are having a component a0, which is basically the DC component. It is not having any frequency component associated with that. However, these sinusoidal signals, they are having this frequency components associated with that. And if you look over here, omega 0, what is it? It is nothing but the fundamental frequency. Okay, it is nothing but the fundamental frequency when k is equal to 1. And if you look into the summation, we are having the harmonics of this fundamental frequency associated over here. Okay, so now can you correlate with the definition? So correlation is that any signal xt, and what is the assumption? The assumption is that xt is periodic in nature. Okay, now take us let us take the example of this pulse signal or the square wave signal, whatever you say. Okay, so over here, if you see, this is the genuine signal. Okay, now if you, it is having a frequency of say 50 hertz. Say for example, this square signal, it is having a periodicity, or it is having a frequency of 50 hertz. Now if I take a sinusoid of 50 hertz, it may look something like this. Now if I take some other frequencies which is having some phase difference with that of the original signal, but it is having either the amplitude which is differing or the phase that is differing, then what is happening, if you see, we are getting some what do you call some regions which are tending to be flat. Okay, and when we further increase the number of the sinusoidals, these flat regions, if you see, they are becoming more and more prominent. And when we take a large number of the sinusoidal signals, if you see this reconstructed signal, it is nearly superimposing on the square signals. Okay, but if you see, there are some ripples over here. Okay, so these are called ripples. These are these small corrugations. It is not exactly fitting the square wave, but you are getting some corrugations, and these corrugations, these are regarded as the ripples. Now these ripples, they are quite predominant at the discontinuities. Okay, they are quite prominent at the discontinuities, and this phenomena, it is regarded as the Gibbs phenomena. Okay, this phenomena, it is regarded as the Gibbs phenomena. This phenomena is the phenomena where there is an what you call deviation from the idleness of the signal when it is being reconstructed using a series of sinusoids. Now why this is happening? This is happening because when we are talking about the reconstruction of the signal, during the reconstruction of the signal, what we are doing, we are only taking a specific number of sinusoids. However, when we talk about the square waves or any other continuous time signals, what I said, that we have frequency components that varies from minus infinite to plus infinite. So the frequency components, they are infinite in nature. That means you will be having infinite numbers of sinusoidal signals. But when we are reconstructing manually, so what is happening? We cannot have infinite number of sinusoids, and due to that reason, we are seeing that there would be some deviations, and because of that reason itself, we will get the Gibbs phenomenon or Gibbs effect. Okay. Now you can look into this sawtooth wave also. So if you want to decompose this sawtooth wave, you will be having a fundamental frequency, and then you will be having some second harmonic or third harmonic. Now if you see, there would be some changes in the phase. Okay, there would be some changes in the phase, and due to the changes in this phase, we are able to get a sawtooth wave, sawtooth shape. Okay, so these changes in the phases, they are responsible in creating the shape effect in the periodic signal. Okay. Now coming to the Fourier transform. So what is Fourier transform? So what he was telling, Fourier transform is a method where we can convert the frequency time domain signal into a frequency domain signal. Okay. Now it is derived, or you can say it is a more generalized version of Fourier series. Okay. In Fourier series, we discussed about that the Fourier series is only applicable for the periodic signal, and it only gives us information that these frequency sinusoids, they are present within the signal. Okay, but it is not transforming the signal, hence it is regarded as Fourier series and not a transform. Okay, on the other hand, Fourier transform is a transform. Why it is called a transform? What do you mean by transform? The word transform, it is basically coming from the transformation. What do you mean by transformation? There would be a change in the physical structure, right? So when we talk about the transforms, they change the nature of the signal, and in the case of Fourier transform, it changes the continuous time signal into the frequency domain signal. Okay, it changes the time domain signal into the frequency domain signal. Now over here, if you see, this is the equation that we started, but in that case we assumed that xp, it was our periodic signal. Okay, so this is the equation for the Fourier series. Okay, now for aperiodic signals, what we are assuming that the non-periodic signal or aperiodic signals, they may be assumed as a limiting case of a periodic signal where the period of the signal approaches infinity. Okay, okay, so what does this mean? Does that mean that can we use the Fourier transform for aperiodic signals, or we can only use it for periodic signals? Pardon? Or we can use for both aperiodic and periodic signals. Which one is true? Pardon? Periodic and aperiodic, because we are assuming that the aperiodic signal or the non-periodic signal, they are these non-periodic signals, they are periodic signals having the time period tending to infinity. So what does it say? Say for example, we take a sinusoidal signal like this, right? Now this is the time period, this is capital T, and after this capital T, if you see, it is repeating itself. It is repeating itself. Okay, again if we go forward, it will be again repeating itself. Now if we are having any aperiodic signal, so what we are saying, so which is having some a duration tending to infinity. Okay, so we are assuming that this signal, this aperiodic signal, it is repeating itself after time tending to infinity. Okay, so within this time period 0 and infinity, whether this sinusoid it is periodic or aperiodic, it is also periodic. So by assuming that our aperiodic signals, they are periodic signals, as time tends to infinity, we are converting, or we are tweaking our results and considering our aperiodic signal as a periodic signal. And due to this reason, in Fourier transform, we are able to analyze both aperiodic and periodic signals. Okay, because if a signal is periodic, or if a signal is periodic within the time t tending to infinity, it will also be periodic within a shorter period of time. Okay, now by doing this, what we have done, by manipulating or not manipulating, by doing some assumptions and putting some including some continuous and the differential variables, we got to this equation of the Fourier transform, which says x of j omega, it is equal to integral of minus infinity to infinity x of t e to the power j k omega t dt. Okay, so what it is saying, we are using that xt, which is the time domain signal, and converting it into another signal where the independent variable is omega. Here we are taking independent a signal which is having an independent variable of t, but then by applying this formula we are converting it into a signal which is having an independent variable which is completely different, and hence it is called Fourier transform, because we are transforming the signal. Okay, similarly we also have this inverse Fourier transform. So from here, what we can do, once we get this j omega, we can use this and apply this inverse Fourier transform of this transform formula to get to the xt. Okay, which is again we are going back to the time domain. Okay, so basically we are having a signal xt, we apply Fourier transform and we get to the f of j omega. So this is the Fourier transform, and if we apply the this inverse Fourier transform onto the this frequency domain signal, we get to the time domain signal. So this is the inverse Fourier transform. Okay, so what is the significance of this one? In the time domain signal, if I give you a signal like this, so again amplitude, so can you say what are the frequency components? Because in biomedical signals, the frequency, it plays an important role. Okay, because a change in the frequency can give you information whether there are any pathophysiological conditions or not. Okay, the same thing happens in other fields also. We may be interested in analyzing the frequency component. So by doing this, what it is happening, suppose when we are applying the Fourier transform, we get a signal like this, and herein we will be having some frequency components. We will be having some peaks at specific frequency components, say omega 0, omega 1, omega 2, and so on, and their height will be proportional to the what you call contribution of these frequency components to the original signal. So from here you will be able to find out which frequency is more strongly present in the signal, in the time domain signal, or which is the weakest frequency component that is present in the time domain signal. Okay, now another important thing what you can do is that from here it will be quite easy for you to determine what are your unwanted frequency components. Okay, say for example, when we acquire the biomedical signals, one of the common noise is the power line interference. Okay, and what we can have, by transforming the signal into the frequency domain signal, we can see whether the 60 hertz signal it is present within the original signal or not, and if it is present, we will apply a band stop filter and we will suppress that. Or it may so happen that suppose there is a 100 hertz frequency component and want to just gather that 100 hertz component, then we will go for the this use of the band pass filter to extract the band pass that particular frequency component. Okay, one of the classical example of this band pass filter, it is in your what do you call this heart rate monitoring by Pan-Tompkins algorithm. Okay, by Pan-Tompkins algorithm. So where we have the ECG signals, we acquire the ECG signals. Okay, then after getting the ECG signal, we have to apply a band pass filter, which will allow us in extracting the QRS complex, and herein the band pass filter, it is having a cutoff frequency of approximately 16 to 22 hertz. Okay, so it will allow you to extract the QRS complex components, frequency components, and by analyzing that you can find out the heart rate in a given in the of the ECG signal that has been given to you. Okay, so you have seen in the ECG signal you are having P, QRS, T. Okay. So this QRS complex, it is being extracted by applying a band pass filter of 16 to 20 hertz. Okay. So we will be discussing about this at a later stage. Okay. So again, this is a periodic signal. Again, by using the same signal, if we put these components at specific time intervals, then we can convert it into periodic extension. Okay. Now this is very important. So over here, if you see, this is a system, and we have discussed that in biomedical signals we only use the LTI systems, linear time invariant systems. Okay. Now this linear time invariant systems, it is having a component which is mathematically represented as HT, and it is nothing but your impulse response. Why this impulse response is important? Impulse response is important if you see, then we are giving delta t, which is the impulse input. Okay, impulse signal we have already discussed. What is the characteristics of the impulse signal? The characteristics is that at time 0 it will be giving an impulse. That means when you are giving an impulse input to the LTI system, whatever the response you will be getting, it is regarded as the impulse response. Okay. Now, why this impulse response is important? The impulse response is important because if we give x of t as the input, then our y of t, it will be given as xt convolution of h of t. What is h of t? H of t is nothing but the impulse response. That means in the presence of impulse, how the system is behaving, that we are determining, and then that characteristics of the system, it is being used to determine the output of the given system when we give a signal xt. Now if you see what I have done, I have included a parameter or an operator which I called as the convolution, So this is the convolution operator. The convolution operator in books you may find it as this star, but in many cases you can find it enclosed within a circle. Okay, so this is a convolution operator. Both are correct, but it depends on what you want to do. Now, how Fourier transform can help you? This convolution, it is quite computational hungry. Okay, so you will have to do a lot of computation to find out the output of the system. However, if we convert this xt into its frequency domain component, similarly, if we convert this ht into its frequency domain component, so my output in the frequency domain component, it will be given by x of omega multiplied by h of omega. Okay, so convolution in the time domain, it converts into multiplication in the frequency domain, and vice versa. Vice versa means if you have to do the convolution in the frequency domain, it will be multiplication in the time domain. Okay. Then Fourier analysis of discrete time signals. Uh, the same thing. It is basically the discrete Fourier series. So similar to our previous case, if you see here, we are saying that xn is equal xn. It is made up of a series of sinusoidal components. Okay. Then discrete time Fourier series. So discrete time Fourier transform. So in the discrete time Fourier transform, what happened is that from the discrete time Fourier series, we have seen that this was the case, and then when we convert or get the transform, we get the discrete time Fourier transform over here like this. Now, if you see, it is a summation. That means it is the number of computations will be finite. But if you look over here, IDTFT, so in the IDTFT, what we are having? Integral. And when we are having integral, that means we will be having infinite number of samples. So our digital systems, they will not be able to handle this IDTFT processor. Okay, and due to this, there was a need to develop another transform, which is basically the discrete Fourier transform, which could handle both the forward and the inverse transforms. Okay, so what is the main problem with DTFT? DTFT is it can handle the forward transform because there is a summation, but it cannot handle the inverse transform because there is an integral operation. Okay, there is an integral operation. So please keep this in mind. This is one of the basic questions which is quite often asked in the what do you call in the interviews and in the vivas. Why you cannot use discrete time Fourier transform for handling the digital signals? And this is the main reason. Okay, the reason is in the inverse discrete time Fourier transform, we are having the integral function, and this integral function means the use of integral function means the inverse discrete time Fourier transform will have to handle infinite number of signal components, and hence it becomes unrealizable in the digital domain. Okay. पानी के नहीं लाए. So rest of the things, if you see, all are similar. Now another important thing, if you look into the discrete time, the omega notation, it changes into this, okay, which is the ohm symbol. Okay. So analog signal or the continuous time signal, the frequency is given by this omega, and digital signal or the discrete time signals, you will be having this. So discrete Fourier transform. So this is a very good chart which gives you information what is happening in the discrete Fourier transform. Okay. So initially we started with a continuous time signal. Suppose this is my continuous time signal. Okay. And if you look, if I do the Fourier transform, I will be getting a component like this. Okay, so this says that it is having frequency component in this region. Okay, in this shaded region. Then what we did, we had to sample this signal. So we use the sampling train. Okay, so we use the sampling train, and if you look into this, you are having if you perform this Fourier transform, what you have at frequency 0, because if you see, you are having this as the DC component. Amplitude is not changing. Amplitude remains the same. So what is that? What is that? That is a DC component. And hence at zero frequency, you will be having one impulse. Okay. Next, what you are having is that if you look into this impulse train, there is a small time period, capital T, and it is related to the sampling frequency. And when you have discretized and when you are working in the what do you call, in the digital domain, as I told you, where you are where you what is your maximum frequency component? Your maximum frequency component is 0 to 2 pi or minus pi to pi. Okay, so where your frequency component will be happening, this minus pi and plus pi, they are basically the same point, right? Am I right or wrong? This is 0, we are going here, this is pi, and when you go like this, we are having minus pi. So where this sampling frequency should be there, I told you the sampling frequency should be the highest maximum frequency. Yeah, this is the FM component, sorry. So half of this thing. So we will be having this signal component, this 2 bars at this minus pi and pi. Okay. So at this sampling frequency component. Okay. Now, when you multiply these two, we get this sampled signal. Now, when we have sampled this signal, if you look into the Fourier transform of this sample signal, it has become periodic in nature. Now, before sampling, what I said, we need to band limit the signal. That means we had to apply the band pass filter to restrict the frequency components. Okay, to restrict the frequency component. And because of this, if you see over here, it is said that you are having this mixing of the frequency components. So why we want to band limit? We want to band limit because we don't want this mixing of this frequency component. If you see, this was your original frequency thing over from here. If you see, now due to the repetition, you are having like this. Now, if you do not follow the Nyquist criteria, that means Fs greater than equal to 2 of Fm, these repeating frequency components, they may overlap over here. Okay, they will be overlapping, right? Now, due to that, what is happening? The high frequency components from the original signal will be mixing with the low frequency components of the repeating signal in the frequency domain. So there is a mixing up of high frequency and low frequency components. Okay. In many cases, you will see if your fan is moving at a very high speed, you will find that there is a perception that some of the blades, they are moving slowly, right? So there is a shadow like thing that is also moving. Okay, but what is happening? Your fan is moving at a very high speed, so that is a kind of this process where high frequency component, they are mixing and mixing with the low frequency component and giving us a perception that there are two speeds. Okay, one is stationary speed for the high for the fan which is rotating at a very high speed, but you are getting a shadow like thing which is again rotating but at a much lower frequency. So there is a mixing up of high frequency and low frequency component. Not everywhere you will see, but in some cases you will be able to see it, right? So this phenomena where high frequency component mixes with low frequency component, it is called aliasing. It is called aliasing. And it happens when we do not follow the Nyquist criteria, that means f is greater than equal to 2 of fn. Okay. Now, if you see over here, what we have got, this is nothing but your discrete time Fourier transform. When you applied this Fourier transform, this frequency domain, it was continuous in nature, right? It was continuous in nature. So, what we want now? We want this frequency domain signal to be sampled. Okay. So before sampling the time domain signal, what we did? Band limiting. Now we have to sample the frequency domain signal. So what we have to do? We have to time limit the signal. We have to time limit the signal. Okay. First we did the band limiting. When we are sampling in the time domain, we are limiting the frequency component. Now when we are trying to sample the frequency component, we will be limiting the time domain signal. So we will be multiplying it with a time domain filter. That means we will be taking up only a portion of the signal, okay, and the rest of the signal components, they are put to 0. Okay. Now similarly over from here, when you get this, so if you get this what you call this Fourier transform of this one, again this is a discrete time signal and you get a continuous signal. Now what you are doing, you have to do the convolution in the time domain signal, because what we are doing, we are getting this impulse train in the frequency domain, right? So we are doing the multiplication in the frequency domain, so it will become convolution in the time domain. By the similar analogy what we got over here, that at time 0 we are having some frequencies, and at time period minus t and plus t we will be having some amplitude components. Okay. So if you see, we are multiplying. Now after the multiplication of this continuous frequency domain signal with this impulse train in the frequency domain, we get sampled this Fourier series, and in addition we also get the sample time domain signal. But due to the sampling in the frequency domain, the signal in the time domain, it has become what we call repetitive in nature. Okay, it has got repetitive in nature, and hence there is a need for the time limiting, so that we can just extract the original signal from the time limited version. You're getting my point? Now under this condition, if you see, we are having both the time domain signal is a both the time domain signal and the frequency domain signal, both of them, they are discrete in nature. So when both of them, they are discrete in nature, that means our digital systems, they will be able to handle the thing. Okay, and this is the basis of our DFT. Okay, here we were talking about DTFT, and here we are talking about DFT. So this is the equation of the DFT and the IDFT. In both the cases, if you see, we are having summation notation. Okay. Now xk, k is the frequency component. It is given by summation of n equals to 0 to n minus 1 x of n w kn n, where n is the length of the signal component. When we are telling that we are time limiting the signals, that means the number of the signal components will be finite. Okay, so we will be having signal component from say 0 to n minus 1. So the length would be capital N. Okay, so length of the signal is capital N, and it will be having the signal components will be present from the time duration 0 to n minus 1, and this wn wkn and small n, it is regarded capital N, it is regarded as the Twiddle factor. It is regarded as the Twiddle factor, and Twiddle factor, it is given by e to the power minus j 2 pi k capital N. Okay. Now, what are these k and n? This small n, what is it? This is the time index. What is the small k? If you see small k is here, this is the frequency index. Multiplication of time index and frequency index. And when we are having wk capital N, so if you see minus j 2 pi k divided by capital N. Okay, so this n at this bottom subscript, it is basically suggesting that this total factor is equal to e to the power minus j 2 pi k by capital N. And if you see, we need wkn by capital N. So when we have this small n over here, it also gets multiplied over here also. Okay, so we will be having e to the power minus j 2 pi kn by capital N. Okay, and what is j? J is equal to under root of minus 1. Okay, now how do we get this Twiddle factor? How do we get this Twiddle factor? Okay, so we get the Twiddle factor in this format wn. So we'll be making a diagonal line, and we'll be putting n equals to, and k will be equal to, in the column wise format, it will be 0 1 2 3 minus 1. Okay, and here it will be 0 1 2 3 and minus 1. Both will be symmetric, because if we are taking say 4 number of signal component in the time domain, we will be getting 4 number of frequency domain component. Okay, so both the values of k and n will be same. So the matrix that you will be getting, it will be having n cross n dimension, capital N cross n dimension. Okay, it is the length of the signal. So w capital N you will put everyone, and now you will start multiplying 0 multiplied by 0 0. So since this row is 0, so everything will be 0. This column, it is 0, everything is 0. You are getting my point? Similarly, if you see 1 multiplied by 1 1, 1 multiplied by 2 2, 1 multiplied by 3 3, 1 multiplied by n minus 1 is n minus 1. Okay. Similarly, 2 multiplied by 0 0, 2 multiplied by 1 2, 2 multiplied by 2 4, like this you will go on. Okay, so from here you will be able to get the Twiddle factor matrix. Okay, now why this Twiddle factor matrix is important? Because if you see, if I want to get the DFT, what I have to do is that I have to take this Twiddle factor matrix and multiply it with x of n. Now see over here, x of n, how it is being represented, x0 x1 x2 and this way. But while we write this signal, when we write the signal, how do we write? We write it as xn equals to x of 0, x of 1, so on, x of n minus 1. Are you getting my point? How we are writing? In the question, you will be given in this form, but while writing it, you have to put it in the column wise manner. Okay. So we will be having xn equals to wn, which is the total factor matrix, multiplied by x of n. So Here we have the matrix multiplication. Okay. On the other hand, while calculating x of n, what we have, 1 by capital N multiplied by conjugate of total factor matrix. So once you get the total factor matrix, you can get the conjugate. What is conjugate? I hope everyone knows. Yeah. A plus JB. If you are having something like this, its conjugate would be A minus JB. Okay, and vice versa. So you have to calculate the conjugate of the total factor matrix xn, which is the frequency domain signal component, and you will be getting the IDP. Okay, so it's pretty easy. So you have one matrix, you multiply it with the signal, you get the DFT of the signal, you directly go to the frequency domain signal. If you want to go back to the time domain signal, 1 by n multiplied by total factor matrix conjugate, then x of n ID, also that will be your IDFT. Now the thing is that how do you calculate this total factor? Okay, so calculation is also very easy. So if you see, okay, let's stop here. So the next class we will be discussing about this total factor matrix calculation. Any doubt? It's pretty